So, today we will start another application which is the recommender system, and this is quite popular not only in the context of graphs, but also in general, right. And I think I have mentioned this thing multiple times that recommender systems are useful for e-commerce services like Amazon, Flipkart, where products are being recommended to users. It is also useful for say movie recommendations, right, or say restaurant recommendation, and so on and so forth. So what is the task? If you think of this task carefully, this is essentially a link prediction task. Okay, we discussed in chapter 6 what is link prediction. So any recommendation system, right, can be modeled in terms of a bipartite network, where in one partition you have users, another partition you have either products or movie or restaurant, right. And if say let us say this is user and this is product, and if this user has already purchased this product, you can connect the user with the products, right, and so on. And what is the task? Say let us say given this user, what would be the recommended products. So essentially say if this user has already bought, right, say this product and this product, so that then these links have already been created. So if you are going back, if you are going in the past, and if you are going to the past, and let us say in the past you had seen that this user had not purchased anything so far, right. Now if you could correctly identify these two products for these users, that would be your success, right. So this is recommender system, and it can be used for a variety of purposes, not only for recommending products, but also for predicting the rating of a product, right. Given a user product pair, what would be the rating that this user is going to give to this product. Okay, this also comes under recommender system or recommendation system, right. So as you see here, a cartoon example, there are two users, both these users have already watched these two movies and they are quite similar, and this lady has already watched this movie, therefore this is highly likely that this movie can also be recommended to this guy, because these two users have kind of similar interests, similar movie choices, right. So recommender system, in short RS, right, it's an extremely studied problem, right. It's been there since last I think 15-20 years, right. In general, if you think of approaches, the approaches can be broadly categorized into three groups. So first one is content based approach, right. Now you can think of if you have historical data, say user product purchase data, you can think of a matrix where rows are users and columns are products, right. Say this is user 1, this is 2, this is 3, product 1, product 2, product 3, 4, 5, 6. If this user has purchased this product, you can write 1, otherwise 0. In fact, you can also write integers which indicate the number of purchases, right. Let us say it is a binary, right, something like this, right. So in a content based recommendation system, the idea is that the philosophy is that please show me those products which I like, right. So in content based recommendation, we look at individual content, right, individual products, and we also look at how this particular user has purchased other products, and depending on that we recommend, right. we will not look at the purchase pattern of other users. Whereas, if you think of collaborative filtering, this is another approach. Here the philosophy is that show me more what my peer likes, my friends like. Okay. Say for example, we already know that this user and this user, these two users are friends, right, because say they have very similar purchase pattern and so on. So, if you and let us say user 1, user 2, user 3 are friends, they have very similar purchase patterns. So, if you want to predict, if you want to recommend products to user 2, you will look at the purchase patterns of user 1 and 3, and depending on that you recommend products to user 2, because the idea is that the recommendation depends on the behavior of a user's neighbors, right. So, it's very natural, right. Say for example, say on Amazon, right, or see in fact movie recommendation, say IMDb rating, right, or Netflix recommendation. Say when you want to watch a movie, so you want to watch a thriller movie, right, you can, what we generally do, we generally talk to our friends who are close, right, quite close friends, and we ask, hey, have you seen this movie, have you watched this movie, and if somebody says yes, I watched this movie, you should also watch this, so I will definitely go and watch it, right. But if I say I want to watch a movie and I ask my friend that have you watched this movie, and my friend says yes, I have watched, but it's not that good, it's okayish, so that would motivate me and that would possibly lead me not to watch that movie again. Okay. So, it is more of a collaboration behavior. The third one is more of a knowledge based recommendation. So, here the philosophy is show me according to my need, right. So, for example, I want to make breakfast, right, I should be recommended say bread, milk and egg, because it should be known to the recommendation engine that I generally take bread, milk and egg in my breakfast. Therefore, there should be a knowledge graph or knowledge base based on which I should be recommended. Okay. All right. So, why recommender systems? In fact, I have already discussed. From user's perspective, it basically helps find relevant items, it helps browse effectively, it enables user to help each other, right, if you think of collaborative filtering. From seller's perspective, so if you look at the product sale, right, you always see that there is a skewed distribution. There are very few products, right, there are few products which are there are a lot of products which are less popular, right, and there are very few products there are very few products which are a lot of which gain a lot of popularity. So, we generally see this kind of long tail distribution, and the problem is to sell these kind of products. So, if you keep on recommending these products, right, ultimately your skewness will increase, right. So, there should be a balance, of products which may not have been purchased by users in the past, but they are actually good, right. So, those products can also be recommended. Okay. In fact, recommendation, searching, these are very relevant, right, as you can understand, right, but there is a slight difference. In searching, the user knows exactly what he is looking for, okay, whereas in case of recommendation, user may not know what he is looking for, right, and when a new product is recommended to somebody, so it may happen that the user does not have any idea about that product. but when the product has been recommended, the user likes the product and he also recommends that product to his neighbors or friends, right. So, here the need is well known, whereas here the need may not be known, right. Now, if you know the need, say for example, you want to buy a Dell laptop. So, you type Dell laptop, all the products will be recommended and you choose one of the products, but it may happen that while searching for Dell laptop, you suddenly see a Lenovo laptop which is even more attractive and you end up buying the Lenovo laptop rather than buying the Dell laptop, right. So, that is recommendation. So, it is also about discovery, right, it is also about discovery. Now, when you talk about discovery, there is another related term which often is being referred to, it is called serendipity, right, serendipitous search. Serendipity is a phenomena which basically says that when you are looking for something and you end up getting a completely different product or entity or searched item which you liked, right, at the end of the day, and this the end product has nothing to do with the search term that you gave earlier, right, that is called serendipity. It's a completely unorthodox discovery. Say for example, you are searching for yoga pose, right, some effective yoga pose, and you end up getting a page which talks about cancer, right, and you start reading that page because after all we are all worried about this disease, right, and this is serendipity, right, because you wanted to find effective yoga poses, say for your stomach, for your liver, or for your say breathing issues, right, but you end up getting a page which is completely different, right, but you still get attracted to it and you start reading, right. Well, I am not going into the details of all these things because this comes under information retrieval, but what I will do here, I will specifically focus on graph learning for recommendation system, okay. So, I mean this is at least at this stage you should already be convinced that why graph is important, right. Graphs basically give you a perspective of this interrelations, interdependency and so on. For example, you see a bipartite graph of users and products, but here users it is not a normal bipartite graph, because here users are also connected in terms of some links. It can be friendship links, it can be some other social relation, whereas products are also connected based on some categories, some hierarchies, right. And user group and product group, they are connected through different links, say clicks, likes, purchase and so on and so forth, right. And in this kind of setting, what is the task? The task is to recommend a product to a user, right, or predict the rating of a user to a product, right, something like this, which is unknown, right. So, we will briefly talk about a few such methods which take into account the user network, product network, use graph learning approaches, the one that we discussed in the last lecture, and effectively solve this problem. So, what is the problem statement here? In graph recommendation system, the problem statement is we have a graph V comma E. V is a set of items, this can be users or products, and E is a set of relations, say purchases, right. And what is the aim? The aim is to learn a graph learning for recommendation system model, right, something like m theta, that generates optimal recommendation results are with optimal model parameters theta that are learned from the topological and content information. So, you are essentially coming up with something which is a function which is parameterized by theta, which takes into account the graph structure and users behavior, past history, and it basically returns a rank list of products or items. Okay. Let us look at the data that we generally use for graph based recommendation system. We generally model the data with a bipartite network, as I mentioned earlier. If there is explicit interactions, then it is good, otherwise we use some sort of implicit interactions and model it in terms of bipartite network. We also capture the sequential interaction data. For example, for a particular user, if product A has been purchased before B, B has been purchased before C, and so on, then you can think of a sequence like this. Or for a product, if A, user A has purchased the product first and then B, then C and D, you can think of a sequence like this, right. In fact, you can also think of a mix of both these things, right. It is a kind of side information data. You have users, you have products, users have different attributes. For example, say location or date of purchase or bulk of purchase and so on. And for product also you have different attributes, for example, the seller, the delivery person, right, the time of delivery and so on and so forth. So, you can think of this additional meta information as attributes for products and users, right. So, let us look at the first approach. So, to understand the first approach, we first need to understand another machine learning approach called autoencoder. Again, I am not going into details of this comes under deep learning, but what an autoencoder does, autoencoder basically is a neural network, a deep neural network, multi-layers, and you basically feed an input, right. You have some encoder which basically maps this high dimensional input to a low dimensional embedding, and then we have a decoder which maps this low dimensional embedding to an high dimensional output, right. So, and this output is same as the input, right. So, what autoencoder does, in case of autoencoder, the input and output are same. You basically try to come up with a low dimensional representation of this input, right, in an unsupervised manner, because there is no supervision as such. Now, this is autoencoder. There is another related concept which is called variational autoencoder, VAE. So, in autoencoder is not able to produce, so autoencoder kind of stuff is generally used for images, right. But the bad part about autoencoder is that it is not able to generate a new image, right. As you see, the input and output are same, right, but if you use variational autoencoder, it is able to generate a similar new image, right. Say for example, you have one type of dog image as input, you may be able to get another type of dog image as an output, right. And what autoencoder does, again I am not going into details of autoencoder, but what it essentially does, instead of learning the low dimensional embedding, is basically learns some parameters, right. So, the idea is that this latent space follows some distribution, right, and in VAE the assumption is that this distribution is basically a Gaussian distribution, okay. So, in Gaussian distribution, when you it's multivariate, right. So when you characterize a Gaussian distribution, what do you need? You need the mean and variance, right. So essentially, instead of predicting low dimensional space, you are basically predicting distribution, right. In other words, you are predicting the standard deviation and the mean and standard deviation, right. So when you predict the mean and standard deviation, you are essentially you are essentially modeling a distribution, right. So the encoder predicts the mean and variance, right, essentially a distribution, and then from this distribution you essentially you randomly pick. Now this distribution is the distribution of this latent space, right. So whenever you pick anything, any point from the distribution, you essentially pick an entity, right. So from this normal distribution you pick an entity, right, you basically pick an entity, right, and you feed it to the decoder, and then decoder basically produces output, okay. So the good part about variational autoencoder is that it can produce a different image, a separate image, which may not be same as the input, right. So you see here there are encoder, there is an encoder and there is a decoder. Encoder is represented by Q. So Q basically takes an image X and produces a parameterized multivariate Gaussian distribution, okay, essentially mu and variance, right, mean and variance. And then so essentially the task of this Q is to predict the mean and standard deviation of the distribution, and then you basically choose one item from the distribution, feed it to the decoder, right. Here Z is that the item that you sampled from the distribution, and then you essentially predict the same the same object, right. So this is the idea. So if you look at the loss function in variational autoencoder, there are two loss functions. The one is the simple log loss, right. What it basically does, you see here, so this is, so Q is the encoder, right, this is phi is the parameter. So and this takes xi, so you have encoder, xi is being fed here, it produces q phi, right. Now from q phi you basically randomly sample an item z, right, and this z is now being fed into a decoder which is basically p of theta, right. P of theta, it takes this. So given this, it tries to predict xi, which is the input, right. So we basically measure the log likelihood, right, the log likelihood of this output, okay. This is the first loss term, and the second loss term is basically, as I mentioned, it aims, so VAE aims to come up with a distribution which is Gaussian distribution, right, which is basically a Gaussian distribution, right, N Gaussian distribution. So it tries to see how good is the distribution that you obtained from the encoder and how it matches with the Gaussian distribution, right. So it is basically a KL divergence between the the Gaussian distribution, mean 0, standard deviation 1, and then okay. Now the same idea has been used for recommendation system using graphs. Now this is called graph convolutional matrix completion problem. You can think of this item, user item matrix, right, and what you do, you basically pass this matrix through a GAE, right, graph autoencoder types model, right, and then you basically try to predict the the missing items, for example this item, this item. So it, what it does, it basically reconstructs this one, right. If you look at the loss function, right, it is very same as the one that we mentioned earlier. Here the input is your A is the adjacency matrix or whatever this matrix, right, user item matrix, and then you basically you come up with a distribution, right, and then you randomly sample an item, right, feed it to the decoder, measure the log likelihood, and then you have a KL divergence side by side, right. So at the end of the day you will essentially get I mean a modified version of this matrix, is user item matrix, and basically those items, those entities which were 0 earlier, right, it can have some numeric, some integers, right, here, and then you use these integers, right, you use these new predictions for basically recommendations, right. So there is another graph based recommendation system which basically uses the graph sage algorithm that we discussed earlier. So what is graph sage? Basically it is an inductive learning, graph learning approach we discussed in the last lecture, last chapter, and what it does, it basically for every node it looks at the neighbors. You can look at k hop neighbors, k goes to 1, k goes to 2 and so on. So you decide this parameter k, right, and you essentially come up with kind of a subgraph of a particular node, and then what you do, you now that subgraph is your input, right, and what you do, so the features of the neighbors are basically aggregated using some aggregated function, and then you do some convolution operation and then you pass it to the next node and so on and so forth. So it's a kind of a generic approach, I mean which turned out to be better than say GCN, other graph convolutional network type approaches, and the good part about this is that it is inductive. So for a given for a new new node, it should be able to produce the representation. So if you look at the graph sage loss function, it essentially maximizes the similarity between neighbors, right. Let us say U and V are neighbors, this is the dot product. So you maximize the similarity between neighbors and you minimize the similarity between nodes which are not neighbors, right, you see here, right. So essentially for non neighbors you do you do negative sampling, you sample out non neighbors, you take the dot product, you try to maximize it, you basically try to maximize the similarity, minimize the similarity, maximize the distance, and you try to minimize the distance or maximize the similarity for neighbors, right, for neighboring nodes. The same idea has been used for recommendation system in this paper. This is inductive graph based matrix completion, IGMC. Again, I am not going to details of this, but the idea is that you have this user item matrix, and from this you basically for a given user, right, you basically come up with an enclosing subgraph. Enclosing subgraph is basically a nearby subgraph around that particular node, and then you run GNN based approach. You can use graph sage kind of approaches, and then when then you get the representation. Whenever a new node comes in, you can easily use the pretend graph sage and then comes up with representations and then predict the likes or ratings or directly recommend products. So if you want to know more about this, more about recommendation system, this is the survey paper that you should look at. These are just some other materials that you should also look at if you want to know more about it, more about graph based recommendation systems, and graph based graph based recommendation system, GBRS. This is very popular these days because of the the effective usage of graphs, right, that you can basically leverage in the recommendation system. That brings us to the end of this chapter. In fact, that brings us to the end of this course. Okay. So, in the next lecture, we will formally conclude this course with major takeaways and some interesting discussions. Okay. Thank you very much.